Uh, Thanks a lot for inviting me to this conference and putting together this excellent program to local organizers. So, uh, Laura made my job a lot easier by giving all the introduction about gravitational waves. I'm going to talk only about the detections, particularly the detections from LIGO-Virgo-KAGRA. So I'm going to begin with some basics of LIGO-Virgo-KAGRA, go over to the LVK detections, and then finally talk a bit about 3G and in particular the Einstein Telescope. I'm not going to focus so much on space-based detectors, but I believe there are other speakers here in this conference who are going to touch on that as well. So to align ourselves to make sure that we are all on the same page, we currently have four gravitational wave detectors which are taking data. The two LIGO detectors in Livingston and Hanford in the US, the Virgo detector in Italy. The KAGRA detector, it was taking data for some time for the last half or for the very last part of '03 and for the early part of '04, but it's once again being upgraded so that it can reach its sensitivity. There are plans of the LIGO India detector to join the detector network, but that will be a few years down the line. This is the current generation of gravitational wave detector networks, the LVK, the LIGO-Virgo-KAGRA gravitational wave detector network. So we have had three observing runs from which all the data is public. The fourth observing run it started about 2 years back, and data taking is still going on. The first set of papers are expected to come out in a few months, and the run is expected to continue until the third until October or so this year. So from all these observing runs, we have detected about 90 compact binary coincidences, mergers of neutron stars and black holes, and we have from the fourth observing run, from which the data is not yet public, we have, including everything, we have a total of 293 detection candidates. This is also including the published detections from the previous runs. For those of you who are not from the gravitational wave community, what you'll see again and again is this typical sensitivity curve, which tells us our sensitivity at a certain frequency. This is the noise curve, actually. So where the noise is the lowest, our sensitivity is the highest. It's around a few hundred hertz or so. So the gravitational wave sources that we expect to detect in this range of frequencies, they fall in four categories: the compact binary mergers, which we are already observing, but there are other sources which we have not observed yet, and searches, they go on for all these kinds of sources. The search categories are slightly different for the shorter and the longer duration sources, as well as for the transient sources and for the longer term sources. So they fall into this kind of an array where we've detected already the compact binary coincidences. There are unmodeled sources, for example, from supernova explosions, which give out a burst of gravitational wave radiation, which cannot exactly be modeled. Then there are spinning neutron stars, which give out a approximately sinusoidal gravitational wave radiation, also approximately at a certain frequency, where the advantage is you can bring together a lot of data, and you can add up the contribution of this tiny source from really huge data. There are some talks about this as well, I believe. And we have the stochastic background, which includes the cosmological stochastic background, kind of expected to be tiny at these frequencies, but also the astrophysical stochastic background, which comes as an incoherent superposition of all other kinds of gravitational wave sources. I will mainly focus on compact binaries. For compact binaries, as the binary merges, it sweeps through a range of frequencies because it's also rotating faster and faster as it's merging. And you typically see in the frequency domain a waveform that sweeps through the pattern and then merges at some time. For shorter, for heavier signals, they merge at a lower frequency. You see shorter chirps. For lighter sources, you see it in the frequency band for a much longer time. You see a much longer chirp, as was the case in this for this particular signal. In the frequency domain, they sketch a chirp, a signal whose frequency keeps increasing with time, much like the chirp of a bird. So the searches are performed at there's the searches for compact binaries which are performed at low latency using template banks that are generated using waveform modeling, both analytical as well as numerical waveform modeling. With these template banks, you run the templates through the data. Wherever there's a match of the template with the data, you see some kind of spike, a coincidence, a spike. If you see spikes in multiple detectors, you call that a coincidence, and from that you can try to rank all the candidates. These searches go on at low frequency as well as at low latency as well as at higher latency, which eventually yields various statistics of the source that we have, of the signal that we have detected in the data. Following the search, when we have identified important stretches of the data, we try to look for the actual source which produced the data. We perform a parameter estimation. This happens also at a low latency, or when a low latency sky map is published, and following that at a higher latency, which often takes quite a few months or 2 years, quite a few months to finally come up with all the parameters of the system, and downstream lies the fundamental physics, astrophysics, and cosmology implications, which I'll touch upon a little bit. What you also see these days at low latency are some numbers. Some of the numbers that pop up are the signal to noise ratio, which tells us how loud the signal actually is with respect to the noise. The false alarm rate, which tells you how likely it is that noise in the detectors could mimic a signal like this, and an astrophysical probability, which also folds in some astrophysical assumptions on top of all of this. Okay, this was a very quick introduction to what comes out of LIGO-Virgo-KAGRA data. I'll move over to current observational results, starting with the first observing run, and of course the big discovery, GW 150914. So we should remind ourselves that it was a number of key firsts. It was the first direct observation of gravitational waves. Not only that, it was the first direct observation of black hole. It was the discovery of a class of heavy black holes of mass around 30 solar masses or greater. Before this discovery, if you ask somebody how heavy is a black hole, how heavy a black hole is, their answer would be, oh, it's maybe about 10 solar mass. Nobody would even speak about 30 solar mass black holes. It was the first observation of a black hole in a binary. Before that, we were not sure whether black holes could form, whether compact black holes could form binaries. And it was the first observation of a black hole forming. You could see the two black holes merging and a third black hole forming, and you could you could actually see what kind of radiation it gives out as this black hole is forming. The highlight of the second observing run was, of course, the multi-messenger observation, GW 170817, the merger of a neutron star, which stretches in the frequency band for almost a minute or even longer. So right after the chirp, you see a gamma ray burst 2 seconds within the gravitational observation. So this gives birth to multi-messenger astronomy. Very quickly, the region is followed up, and in about 10 hours, you detect an optical counterpart, which slowly fades away into the near and the far infrared, eventually emitting radio afterglows. This is the birth of multi-messenger science with gravitational electromagnetic waves. It also has a number of key firsts. It confirms BNS, binary neutron stars, as progenitors of short GRBs. Which was only a conjecture until then. It demonstrated this as prolific sites of heavy element formation in the spectral lines of the so-called kilonova. You could see signatures of heavy elements, in particular elements like strontium could also be identified there. It constrained the speed of light with respect to the speed of gravity. So the gravitational and the electromagnetic signal arrived almost at the same time after traveling for 100 million years. It provided the access to the neutron star equation of state. There were many equations of state which were in vogue back then, which really got killed with one single observation. And it provided a novel measurement of the Hubble constant. As we move over to the subsequent observing runs, we start probing various different corners of the parameter space of compact binaries. For example, we observe this detection 190425, in which one progenitor is in which one of the for which the total mass is much higher than in the total mass of any neutron star binary that is observed in the galaxy. Unfortunately, this BNS merger did not have a counterpart. Then we have this 1908-14, in which the lighter object is sitting in the mass gap between neutron stars and black holes, and which also has a rather high mass ratio. Then we come to this 1905-21, where you see black holes whose masses in the source frame are as high as 85 and 66 solar masses, and for which the total mass is almost 150 solar masses, which would clearly be classified as something called an intermediate mass black hole. In O4b, we start detecting neutron star black hole mergers. So here in colored contours, you see objects which are certain to be neutron star black hole binaries, and in gray contours you see objects which could be neutron star black hole binaries because one is not very sure about their masses. And in one single observation of O4a, the fourth observing run, which has already been published and which was also mentioned by Laura, we came up with an observation that lay bang in the middle of the neutron star and the black hole mass range, closing the mass gap between neutron stars and black holes. So of course, we have many exciting single events, but we also have a population of events. We have 90 such events. And with a population of events, we can do a lot more science often than with single events. For example, we can do tests of generativity, and certain tests of generativity, they benefit from the fact that you can combine information across multiple events. And here's an example where you can constrain the mass of graviton to precision which is much stronger than the precision to which you can constrain the mass of the photon. Here you see the mass distribution of the observed compact binaries, where you start seeing features in the mass distribution. And finally, here is the most up-to-date measurement of the Hubble constant, which also improves if you can combine information from a number of events. And all of these aspects are going to be covered by some of the speakers here, respectively Chris van den Broek, Michela Mappelli, and Nicola Tamanini will be talking about fundamental physics, astrophysics and cosmology results from these observations. The fourth observing run is currently going on. Actually, now we have a month or two of commissioning break, so the detectors are down since the beginning of this month. However, we are in the O4C, the third part of the fourth observing run at the moment, and most of the detectors are for most of the time, Livingston, Hanford and Virgo detectors are operational. So we are operating as a 3 detector network. Livingston and Virgo operating at around 100, sorry, Livingston and Hanford operating at around 150 megaparsecs, and Virgo operating at a much lower sensitivity of about 50 megaparsecs of BNS range, the distance up to which you can see binary neutron star with this particular detector. Of course, you can see binary black holes to much farther away. So with this very limited sensitivity, Virgo is already contributing significantly to the